Meta's last earnings conference call, CEO Mark Zuckerberg said that AI is going to change advertising in a big way.
It is very true that Meta has been investing heavily on AI and advertisements. The main reason for that is Meta makes most money from their advertisement business, and advertisement has a lot of potential with AI. There are multiple areas where AI and advertisements can benefit. One of them is around the generative AI space where you are generating the advertisements. Another area is around the bidding and auction space where using AI you can automate these auction processes. And in this video we're gonna dive into the AI auction space, look at some of the design and research done in this area and how we can do a system design which generally gets asked in the interviews for this specific use case. So let's get started. So let's first try to understand how programmatic auctions actually work. There is this video from Trade Desk that explains the concept pretty well. So let's look into it.
When the page is loading, the container or ad space is rendered, and a request for an ad is sent to that exchange. The exchange sends the request for bids to all registered demand-side platforms, or DSPs, which are companies like the Trade Desk that represent the interests of advertisers, to fill the ad slot with creative that is relevant to the audience at that exact moment. When a bid request is received, each DSP sifts through hundreds of pieces of metadata about how, where, and to whom the ad will be shown, and decides what the opportunity is worth to its advertisers. An advertiser's level of interest is translated into a bid and is submitted to the exchange where all bids are auctioned. The highest bidder wins and their ad is sent to fill the original container. All of this happens in about 1/10 of a second.
Initially, the programmatic auction started. There were a lot of complexities because there were multiple ad exchanges, multiple DSPs. They all have their own formats for bid requests. And an example could be geolocation. So a company like Google has its own way of representing a geolocation coordinates. AppNexus and others have different ways. To address this issue, IAB created a standardized protocol that enables real-time transaction of digital ad currencies between advertisers and publishers, and this platform is called OpenRTB. So this is how the auction process works with OpenRTB. So it's very similar to what we discussed. So there is the main key components here as the demand side platform and the sell side platform. So generally when we are designing, we need to understand the functionality of each of these components. So the main functionality of DSP includes like a request processing. So it has to parse these requests that are coming with requests. The other one is around the user information. So there is a campaign ID as well as a user ID that is associated, kind of maps those with the database. It has to also make sure that the requests are compliant. So it checks for the CCPA and GDPR compliance. There is bidding engine, which is one of the key component here. The bidding engine responsibility is to do real-time bid calculations, campaign eligibility checking, budget management, and creative selection. And then from the analytics side, a lot of machine learning work is done around performance tracking, bid landscape analysis, and try to optimize the win rate as well as spend analysis. There are two kinds of auctions. One is the second price auction. In the second price auction, when multiple DSPs submit their bid request, the one that puts the highest price is the winner, but the price that they have to pay is 1 cent more than the second highest price. So in this case, DSP1 is the winner, but they're gonna pay the price of the second highest bid, which is 9.50 plus 1 cent, which is $9.51. So this is the case of second price auction. In the first price auction, you basically just pay the highest price. So in this case, it will be $16 for the first SSP, and the second SSP is gonna pay is $12. So from a publisher point of view, the maximum of the two is 16 and 12 is 16. So the publisher gonna sell the ad for $16, which is great. So they're gonna make around 3.99 profit over the second price auction. This is a new model which Google started, and everyone has started moving towards this model. So this will be the focus of this particular call. Now to identify the right bid price, DSPs apply machine learning and data science. So predictive clearing. So the idea here is that there is the true value of the ad and that there is the market value of the ad. So what DSP tries to do is to find the bid price, which will be somewhere in the middle of the two, and the closer they are to the market value for the bid price, the more savings they will have, but the win rate will go down. So because so the idea here is to identify this value of X that will help us maximize our profit. So the optimization strategy here is to identify the right bid price. So as the input, you'll get the bid request with user information, ad information, etc. So in terms of machine learning, we'll design a function to optimize the advertising key performances, considering the budget constraint. The KPIs could be CTR, click-through rate, conversion value, etc. So this was taken from University College London webpage. So these are the strategies that DSPs can take to optimize the bid price. The main here is the bid calculation, bid landscape, and budget pacing. So we'll discuss these in details today. So the idea behind bid optimization is pretty simple. So what we tend to do is maximize the difference between value and cost, which is our profit, right? And value can be derived from like click-through rate and the conversion rate. So if the conversion rate is CR and the value per conversion is V, so the whole value function will be CTR BT into CRV, and similarly the cost function will be the click-through rate for auction T and multiplied by the cost per click. But the thing is that this should be less than the total budget. So what we try to maximize is this function here, which is less than or equal to the budget B. So the first optimization technique that DSPs generally use is bid shading. So the idea here is to place a bid that is below what the item is worth. Mathematically, you can represent bid shading with this formula. What we try to identify is the shading factor here, and we try to maximize the expected utility function. The idea here is to find the optimal balance between winning probability and probability margin, profit margin. So you can use any regression-based model to solve this equation. I personally have used XGBoost and has given good results, so I would recommend using that. Mention to your interviewer that alternatively you can use linear regression model. It's simple, but it doesn't capture the complex interactions between features like XGBoost does, especially when handling non-linear relationships. Another model that comes to my mind is like random forest regressor. It's typically slower and less interpretable as compared to XGBoost, and it's good for smaller data sets, but when it comes to large data sets, the scalability becomes a problem. So this is all the research that has been done in the field of bid optimization. As you can see that the move has been from rule-based models towards reinforcement learning in terms of the optimization techniques. And in terms of the problem complexity, previously it used to be mostly single constraint. Now it is moving towards a multi-agent based approach. Unlike single agent systems that operate independently, multi-agent systems orchestrate multiple AI agents to work together towards a shared goal. As we shift towards first price auctions, a lot of research has been done in that area. Mu is an important paper in this area. It's a space-efficient non-parametric bid shading algorithm. I found the presentation from Way online for this paper, so let me show you what it is, and you can download the full presentation from the link in the description.
I will introduce the algorithm part. It is called multi-resolutional exponential weighting, the MU algorithm. We allocate all data points into small bins horizontally by the valuation of the object, and in each bin, we also vertically divide the bidding price levels and keeps record of the cumulative historic reward for each bidding price, denoted by Sij. The non-parametric algorithm makes one decision in each bin by the probability proportional to the exponential of Sij. This is grounded by a theory paper that shows that this algorithm leads to an optimal regret with almost no modeling assumption. And in this paper, we make the algorithm data-driven and thus significantly improving both the efficiency of storage and calculation.
Another important algorithm is the dynamic floor pricing algorithm. The idea here is to minimize the acceptable bid price based on real-time conditions like user information, ad inventory, and competitor bidding behavior. Another important strategy that I can think of is the meta model approach, where you try to aggregate the output of different models, such as the price prediction model, win rate prediction model, and value estimation models to generate the best bid for each action. For dynamic flow pricing, logistic regression could be an approach. The output of logistic regression tells us that the likelihood of winning, and based on that, we can identify the bidding strategy. For example, if we know 75% of the chances of winning, we must adjust the bid in this case. Another approach that I can think of is follow the regularized leader approach. It's an online algorithm that combines the benefit of traditional gradient descent models with efficient handling of sparse data. So you can see the term for L1 regularization for sparsity and L2 regularization for stability. The approach is factorization machine. A factorization machine models all possible interaction between variables using factorized parameters. The matrix represented as a product of smaller matrix.
What the factorization machine is. In the end of the day, you're going to end up with a sparse vector of features, of real valued feature vectors. The prediction of a factorization machine is going to be the linear part plus the interactions. And then because that interaction is symmetric, it is enough to look at the upper diagonal of the interaction between xi and xj. So a linear part plus a part that is supposed to model the nonlinear part. And if you guessed that you are going to replace this part by a deep neural network, you guessed it correctly. So learning both low-level and high-level interactions. Have a prediction coming out of your factorization machine, which is this branch. The other branch is your deep neural network. And then you're going to simply add them and then push them through a sigmoid to give you a prediction. Is the user going to interact with this item? Yes or no? The factorization machine part is very similar to before, and these are your representations for each field.
This is a very high level architecture of the system. The main components here is the real-time system that handles all the real-time information, how to scale the system, how to handle millions of requests per second, and then the analytics part of it, which is basically identifying the right bid price, identifying the right algorithm for optimizing your bid requests, etc. This is a very high level data science overview. So let's say Fiona is playing a game and then the ad shows up. 1 million ads are there. They have to make an ad selection. So what happens in the background is there is a small model that is running. It's a simple model that identifies 1000 ads, and then there is a complex model that identifies very unique specific ads to the user. Then the auction happens and the ad is served. Scale of ad tech is huge, roughly 200 milliseconds per response in real-time bidding, 40,000 requests per second, 400,000 model predictions per second, and 300 million events per day. So this is a rough estimate, but you can see the scale of ad tech here. Very high-level architecture using AWS. So the ad exchange request, bid request, and bid response are handled by the bidder service in AWS, and then all the requests get stored in the database. And then there is a event tracker service which basically monitors how the user has reacted to the ads by impression, clicks, installs, etc. And all these are tracked through event tracker service and then get stored in the database as well. This is a very high level architecture of the bidding system. You can see there is a Respike database, so it stores all the user information and all the request response events. Respike is great for lightning fast performance because it can store millions of requests per second. And then it is connected to the Spark cluster. Spark is used for data preparation in feature engineering. Once that is used, it can be directly used by the exploratory data analysis tools. Once the model is ready, it is trained, and then some A/B testing is done on the model with performance tuning and other approaches. And then once the model is validated, it is ready for release to production. It is being served on the APIs that we have built using AWS. And then the ML application kind of consumes these models. So this is a very high level machine learning model architecture for bidding system. This architecture is highly scalable. If we include Kafka in it, it becomes a real-time bidding service architecture. So yeah, this can be used in machine learning interviews, mostly related to system design, kind of covers data science and engineering aspects to it. Hope you enjoyed the video, hope you liked the video, and don't forget to like and subscribe.